Well, now I'd like us to consider some torque or moments that cause round things to rotate. We've considered forces pushing and pulling things, forces of friction that make things rotate. In this situation, we have a wheel that's on the ground and it's being driven by a motor or some sort of torque around the axle that's causing it to rotate or makes it want to rotate in that direction. So that's given as that moment right there. Well, if there was no friction at the bottom, and anybody who's jumped on the gas in your car in a snow pile, you know that the wheels just spin. Well, doesn't get us very far. So what we know is that in order for the vehicle or this wheel to go in this direction, there has to be something making it go in that direction. And that is not the torque specifically, it's the force of friction that makes it go that way. So when we draw a free body diagram, we have an mg coming down, we have a normal force here, and we have a force of friction that goes in that direction, and that's being driven or helped by that moment. All right, so in this little problem, we're going to assume a few things. We're going to assume the mass is 50 kilograms and the radius of gyration is 0.375. And what we want to do is find out the speed at 20 meters. At the beginning here, we're going to set the mu of 0.6, and at that we're going to assume, we're going to check it later, but we're going to assume that it's a not slip condition, and when there's not slip condition, we know that the force of friction does not equal mu normal, but A does equal R alpha. All right, so let's just do our force equations and our moment equation, and we can see how this goes. The only force we have in the x direction is that force of friction, and that's equal to 50 times ax. The moment equation about the center of gravity is going to be 100, which is that driven moment. That's the 100. Now the force of friction is actually going in the other direction, isn't it? It's trying to cause a moment going that way, so I'll say minus force of friction times r is going to be equal to Ig. In this case is going to be mk squared alpha. And if we assume not slip condition, then we show that alpha is equal to A over R. And then we can solve all this then for acceleration and alpha and the force of friction. So not very hard to do that. You can see that those are the numbers, 2.66. Alpha is 6.6 and force of friction is 133. If we take that constant acceleration, which is that, and plug it into a constant acceleration equation, we can see that the speed at 20 meters is going to be about 10.3 meters per second. Now it's important then to check to see if our assumption about not slipping was correct, and we do that by comparing the force of friction to the maximum force of friction which would occur if it was slipping. So we're going to check there, and if the force of friction, or if it was slipping, we would know that the force of friction maximum is equal to mu normal. In this case it's mu mg, and we could say that the force of friction, it cannot be greater than 294 newtons. What we solved for in our equation was 133, which is less than 294, so we can assume that not slip was valid and that our beginning assumption was correct. In other words, we have confirmed that there is no slip. Now, just a very, very common mistake in these torque problems is to think that the moment equals the force of friction times the radius. And that is not the case. That's a static situation where the force of friction and the moment, force of friction times radius and the moment might be equal to each other. But in dynamics, that's not the case. And so here you can see that force of friction times the plus the moment is equal to this side of the equation, the Ig alpha. They're not equal to each other. All right. Now another thing to consider would be a slipping condition. So let's consider slipping in the same problem, and we're going to say that the mass is again the same and the radius of gyration is the same, but in order to establish a slip condition, let's find out what the minimum mu to prevent slip might be. And in that case, we know that the force of friction is mu normal and A equals R alpha at the same time. We can use either the moment equation or the force equation to find out what that minimum mu is. In this case, I'm just using the force equation. I'm going to say that force of friction is mu mg, max. I'm going to use the acceleration that I solved for before, and under those conditions, with this moment and with that moment and the acceleration that I got, I can say that the minimum mu to prevent slip is 0.271 under these conditions. So that if I then consider a slip condition of less than 0.271, so let's say that mu is equal to 0.25. we know that since we found the minimum mu to prevent slip, we know that 0.25 is a slip condition, and under the slip conditions, force of friction is mu normal, and but A does not equal R alpha anymore. I can use my same two equations, plug those things in there, and I solve for each of those values separately in one equation, one unknown situation, so that's fairly easy to solve the acceleration, the alpha, and the force of friction under the slip conditions. All right, now how do we use this to our advantage? That one problem is kind of a just kind of a textbook problem. It doesn't really, it's not real in reality. However, this one is. So here we have a big loader that's being driven in the back by a big motor, and it's going to try to drive these tires in this direction. It's being driven by the back, so it's going to put a torque here. It's going to try to make them go in that direction. And what we know is that there's a force of friction going to be acting in the back, and in the front there's going to be a force of friction making that roller turn. We've already discovered most of that stuff, but let's draw a free body diagram, an exploded free body diagram of this system, so that we can kind of analyze how the forces and the torques act on each other. So let's just consider the free body diagram of the front roller first, and we're going to say that we know that it's going to roll in this direction. We know that it's going to go in that direction, and it's going to roll in this direction. We know enough to know that the force of friction at the bottom of the roller has to be going in this direction to make it have that rotation. And but we know it goes in this direction. So the force of friction is moving in that direction, so I know that there has to be something pushing it that way, and that's going to be the reaction right there in the middle of the wheel, over the middle of that roller, coming from something else. So I'm just going to put a force in that direction. There's also going to be a weight coming from the whole machine, and that's going to be pushing down on there, which is going to help us have some of that. There's going to be an mg of that plus a mg of the roller plus some weight on there, which is going to result in that normal force. All right, so if the force of friction if there's a reaction force here pushing this roller in this direction, it has to be pushing back equal opposite on the body. So these two forces here push back equal opposite on the body, and that's we're going to have that C, which is basically the main body of the tractor, and it's going to be pushing there. It has its own mg, but we know that it goes in this direction. We know it's going to be traveling from right to left, so there has to be something pushing the whole thing here, which has to be a force here at this axle, which is right there in the middle of that axle. So I'm going to say that there's going to be a pushing force there and a pushing up force here to keep that balanced. Those two forces transfer equal opposite to the rear wheel. So here's where the torque comes in. This is going to be driven by a moment. There's going to be a force coming in this direction from the body, force coming in that direction from the body plus its own mg, a normal force here, and we know that it moves in this direction. With this force pushing back, then you know that the force of friction has to be greater than that d, which makes it go that direction. So again, don't want to belabor this point too much, except that if you understand all the forces in the exploded free body diagram, then it's easy to see how the system works together. So the behavior of the system is easily understood when you break up the pieces and do some of the moments and some of the forces analysis for each component, and that's what I just did there. Okay? All right, so when you understand those things, it's really easy then to put the whole picture together, and you can use a composite approach, a systems approach fairly easily. Since these forces all are equal opposite, when you put them, all those forces are all equal opposite to each other. When you put it all together as a system, they basically disappear. So here's what the system free body diagram looks like. We have an mg of the main. We have a torque in the back, a force of friction pushing this way. I should have put an mg coming down here, but then the force of friction in the front has to be going this way, which causes that roller to do in that direction. All right, so what we're going to do then is we're going to use this understanding to do an F equals ma analysis on this entire system. So here we have a problem, and it says that we have a torque in the back of 5,000 Newton meters. That's going to be at the back. It's got each tire has a mass, let me think here, The rear wheels are driven, 2 tires, each has a mass of 500 kilograms in the back, and the front roller has a big mass of 2,000 kilograms with a radius of that. And we're going to model that as a cylinder in the front. All right, so with an F equals ma analysis, here's our look. I got that torque, I got that force, and I'll say that the sum of the forces in the x are going to be equal to the mass times acceleration of the entire system in the x direction. Let's take the, before we get to that force equation, let's look at the moments on each axle. So the front axle has, again, it's got several forces, but the only force that's causing a moment is going to be that force of friction in the front. So the sum of the moments about G is Ig alpha. We know that it is a not slip condition. So A is equal to R alpha, and plugging all those numbers in there, I can get an expression here for the force of friction at A. In the rear, I have a similar kind of thing. Sum of the moments about G is Ig alpha. And in this case, I got the moment causing a force or a torque in that direction. Torque in that direction caused by that moment. And then I have the force of friction going in the opposite direction. So the force of friction times R. And I have 2 tires in the back, so I'll say that that is 2 times the mk squared A over R. And I can then solve for, or get an expression there for force of friction at B. This doesn't look like I solved that. Thought I should have, but anyway, I didn't solve that for force of friction at B like I did there. But what I can do is I can put that, assuming I did solve it, I can put that into a 3 equations, 3 unknowns situation here as soon as I get my force equation. So some of the forces in the x then are going to be equal to, the only forces I have in the x direction are going to be that pushing force back here, and it's going to be resisted by that rolling friction force in the front. So force B minus force A, and I'm going to take all the masses together and find out AX. So here I have a 3 equations, 3 unknowns situation from those 3 equations, and I can solve for AX. And then to find out how fast it goes after 10 meters, I'll just use that constant acceleration equation and find out what the speed is at 10 meters. I can do the same thing with energy. And we're in the energy chapter now, so let's just do the exact same problem with energy and see what we get there. Now remember, with energy, friction forces, rolling friction, does no work if it doesn't slip. So those 2 forces of friction still exist, but they do not do any work because they are in a not slip condition. However, the moment does do work, and the moment is going to do work of moment times the radius, or times the number of radians that it turns. All right. So let's say rear does not slip. So S is equal to R theta here. The work of the moment is m times theta. So let's just see what that is. The work is the moment is 5,000, and the number of radians is going to be the distance divided by the. Here we go. It's going to be the distance divided by the radius, and we get the number of radians. So I'm going to move 10 meters. The radius in the back is 0.6. That's the radius in the back. And so I can see that how much work is being put into the system of 83,333. Okay. And then when we get done with all that work, we're going to have some combination of rotational and kinetic and translational kinetic energies. And so all I'm going to do here is solve this all for T2. So I got 1/2 mv squared of the body, plus 1/2 mv squared of the front roller, plus 1/2 I omega squared of the front roller, plus 2 times 1/2 mv squared of the rear tires. There's 2 of the rear tires, plus 2 times 1/2 I omega squared of the rear tires. You can see the math here and plug all those things in there, and you can find the number when we solve for this. The velocity is going to be the same thing, which is handy. It's nice to know that when you solve the problem in different ways, you still get the same answer. So when you do your homework, I would suggest that you do both methods. When it comes to an exam, I'll let you choose which method you want, either F equals ma or energy, and both of them work, I think, about the same in terms of difficulty and number of equations and things like that, so you can choose which way you want to do that. All right, so let's go back to this, our single wheel then, and let's find out what the speed at 20 meters of this guy is using energy. Same concept again. We're going to go back to mu of 0.6, which is a not slip condition, and we know that the force of friction does no work, and V does equal R omega under those conditions. We know that T1 plus V1 are both going to be 0 because we have no beginning kinetic energy. No beginning kinetic energy. There's no change in elevation and no springs. So the work that's being put in is moment times theta. It's got 100 Newton meters of work, or 100 Newton meters of torque. The theta, again, S is equal to R theta, so we solve that for theta. We're going to move 20 meters and divide that by the radius of this thing is 0.4. Plug that in, we can see that the work put in is 5,000. And then that's going to be equal to 1/2 mv squared plus 1/2 I omega squared. And solving all that, you can see that the velocity is 10.3, which is the same thing we found at the beginning of the problem, beginning of the lecture, using F equals ma. So again, torque is a very valuable thing. We'll be doing a lot of understanding of that as we go forward. Thank you.